Good evening, everyone. My name is Andrew Fracknoy. I'm the Emeritus Professor of Astronomy here at Foothill College, and it's a great pleasure to welcome everyone here in the Smithwick Theater and everyone hearing and listening on the web to this lecture in the 20th Annual Silicon Valley Astronomy Lecture Series. This series of free public lectures is co-sponsored by 4 organizations: the Foothill College Astronomy Program, NASA Ames Research Center, one of the premier NASA centers around the country, the Astronomical Society of the Pacific, a venerable organization doing public outreach in astronomy, and the SETI, the Search for Extraterrestrial Intelligence Institute in Mountain View, and we're delighted to have their support for this series. Tonight's speaker is one of our favorites. I think this is his 3rd time, right, talking to the series, Dr. Eliot Quataert. Dr. Quataert is Professor of Astronomy and Physics at the University of California, Berkeley, and the director of the Theoretical Astrophysics Center there. He's an astrophysics theorist who works on a wide range of problems at the forefront of astrophysics, from stars to black holes to how galaxies form. He's received a number of national awards for his research and is also a highly regarded teacher and public lecturer, as you will see. This is his 3rd talk in the series, and we're delighted to welcome him talking about what does a black hole look like, how we got our first picture of a black hole. Ladies and gentlemen, Dr. Eliot Quataert.
Thanks, Andy. It's great to be here, be back again, and telling you about some of the really exciting results that have just come out in the last year. The picture that's basically the entire focus of this talk is the real one on the lower left here. This is a picture of a black hole, the region around a black hole, that was taken in April 2017 and then released actually this spring. So in April 2019, the observations were released. And really what I want to do over the course of this talk is try to explain to you what we've learned from this image, how it was taken, why it looks like it does, why is part of it bright, part of it not as bright, why is there a gap in the middle where there isn't any light coming, etc. The subject of this talk, black holes, is one of the most common objects for science fiction. Really, since the 1960s and 1970s, when black holes really became a part of modern astrophysics and physics and began to be studied in great detail, they've also become part of science fiction. There are many, many Star Trek episodes where the Enterprise pierces its way through the event horizon or something crazy like that. There's this Disney movie from 1979 about black holes. The most recent, I would say, modern version of black holes featuring in the movies is the movie Interstellar from 2014. This actually, I think, stands out among all of the science fiction movies that have been done about black holes or really on other topics, and that the original screenplay and one of the executive producers for Interstellar was Kip Thorne, who's shown on the right there. And Kip is a Nobel Prize-winning physicist at Caltech, so actually knows some decent amount about black holes. Black holes also show up in slightly unexpected places. This is a graphic novel about teenagers who were cranky and disaffected in Seattle. I don't really know what it has to do about black holes, but it makes for a good image. Just to give you a sense of how much a part of popular culture black holes are, if you go to Amazon and you type in black holes, in this particular case, I got 101,844 results. This was a while ago. I think there's a lot more now. This is actually the graphic novel that I showed you the image of a second ago. This is the Disney movie. This is a nice book by Neil Tyson about black holes, and it goes on and on. There's many, many popular books, movies, TV shows on this theme. Slightly unexpectedly, there's also health and personal care products related to black holes, which are mostly in the area of liposuction and things like that. Okay, so really I could go on and give you an entire talk about how black holes manifest themselves in science fiction, but instead I want to turn really to the science focus of this talk. And what I want to do is I want to try to first explain to you a little bit about what black holes are, how we as physicists think about them, and then how do we actually find black holes out in the universe? How did we end up taking this remarkable image, which really is showing us what happens incredibly close to what we call the event horizon of the black hole, which is the point of no return, inside of which everything gets sucked into the central object. So I'll start with this kind of make sure we're all on the same page, understand what we're talking about when we talk about black holes, and then get into how we actually took this picture. So before we talk about black holes, I want to talk about something that's a little bit simpler, which is the sun, shown here, or the planet Earth, the one we're on. The story about black holes is really a story about gravity. It's a story about gravity really winning at the end of the day over every other force we know of in the universe, causing an object to collapse to form a black hole. But in our everyday experience, in a star like the sun or a planet like the Earth, gravity doesn't actually win. There's a sort of happy balance. Gravity is always pulling inwards. It's what keeps us here on Earth. It's what keeps the Earth together. It's what keeps the sun together. So gravity is this sort of relentless force pulling in on all matter in the universe. But in something like the sun, there's a counterbalancing force. There's something pushing out, stopping the object from collapsing in on itself. And in the case of the sun, it's basically that the sun is a big hot ball of gas. The temperature inside the sun is millions of degrees. It's kept hot by nuclear fusion of hydrogen into helium at the center of the sun, which will keep the sun nice and hot in its interior for billions and billions of years, and able to fight off this inward gravitational pull of gravity. Now, this happy balance between gravity pulling in and something else, pressure in the case of the sun pushing out, that happy balance is one that we know, at least in our everyday experience, it's one that can be overcome, right? The example of this that you know about is that we've been able to successfully launch rockets and satellites off of the Earth and escape the gravitational clutches of the Earth. We've launched Voyager all the way out of the solar system. And we've launched many satellites into the outer part of the solar system. In astronomy, we talk about how hard it is to escape the gravitational clutches of an object by asking the question of, if you were to launch something, throw something off the surface of the object, how fast would you need to throw it in order to escape the gravitational clutches of the object? And we call that the escape speed or the escape velocity of the object. If I were to throw a ball off the surface of the Earth and not throw it very fast, it would go up and it would come crashing back down. If I were to throw it a little faster, it would go up further, come crashing back down. If I threw it just right, fast enough, in the case of the Earth, that's about 27,000 miles an hour, or about 11 kilometers a second, then that ball would actually be able to leave the Earth entirely and travel out into the rest of the solar system. But the strength of gravity depends on how much stuff there is, how much mass there is. It depends on how large something is. Gravity is stronger when things are closer together. So if you have a smaller object in general with the same amount of mass, you'd have a stronger gravitational pull. So every object in the universe, every object in the solar system, for example, has a different escape speed, a different speed that you'd need to throw something, launch a rocket, throw a ball, to escape the gravitational clutches of the object. So for the Earth, it's 27,000 miles an hour, 11 kilometers a second. The sun is much more massive, 300,000 times more massive than the Earth. And as a result, it has a much higher escape speed. So all of those rockets that were so extraordinarily proud of being able to escape the gravitational clutches of the Earth, they would come crashing back down on the surface of the sun, because the sun's escape speed is something more like 1,000,000 miles an hour or 600 kilometers a second. The physics I'm describing to you here, this is physics that was known in the time of Newton. This is really some of the major conceptual advances that Newton taught us in terms of gravity and motion. A little bit later, we also learned that even light actually travels at a finite speed. So when I press on the laser pointer and it goes and it bounces off the wall and then it bounces to your eyes, it actually takes a certain amount of time for that to happen because light doesn't travel instantaneously. It's very fast. It happens in a tiny, tiny, tiny fraction of a second because light travels very, very quickly, but it does take a certain amount of time for light to travel. The speed of light, it turns out, is about 300,000 kilometers a second, or 1 billion miles an hour, or 1 foot every billionth of a second, every nanosecond. So that's an extraordinarily fast speed, much faster than speeds that we're familiar with in our everyday experience, which is why in practice we don't really have an intuition for the fact that light has a finite speed. But this is something that one can measure in various experiments. The speed of light is actually taken to be a constant, a universal constant, in Einstein's theories of relativity. And the first notion of black holes in physics actually arose in the late 1700s. And it arose basically independently by two scientists, Michel and Laplace. Laplace is a very famous mathematician. Michel was actually a geologist who did a lot of work on earthquakes. And what they did is they basically just combined these two ideas that I've just told you. Every object has an escape speed, the speed you need to escape its gravitational clutches, and even light has a finite speed. And they speculated what would happen if you had a star that was so small that the speed needed to escape its gravitational pull was larger than the speed of light. Then not even light would be able to escape the surface of that object. And so they speculated that there might be stars out there, dark stars, that we couldn't see, that wouldn't emit any light because their gravity was so strong that not even light could escape the gravitational clutches of the object. And they actually went one step further. They estimated how large would such an object have to be. The strength of gravity depends on the mass of an object and its size. And so depending on how much stuff you're talking about, the mass of the object, you need a different size to have the escape speed be larger than the speed of light. For an object that has a mass like the mass of the Earth, you would need to shrink the entire Earth down into a size that's smaller than a baseball in order to reach these extreme conditions where not even light could escape the gravitational clutches of the object. The sun weighs 300,000 times more than the Earth. It's a larger mass. You would need to take the sun and shrink it down to about the size of a city, a few miles big, in order for gravity to be so strong that not even light could escape. And this size, the size needed for the escape speed to be about the speed of light, this is what we now call the event horizon of a black hole. So this idea was sort of out there in the late 1700s, but honestly not much happened until the early 1900s, so 130 years or so later. And the reason is that Michel and Laplace basically pulled a little bit of a swindle when they made this argument. And the reason is that the theories that they were using, Newton's theories, don't really apply to light in the way they were using them, and they don't apply when gravity is so strong that it can affect light itself. And so we needed to wait for new theories of physics that could apply in these extraordinarily extreme conditions where gravity is this strong. And that theory is the theories that Einstein developed. His theories of relativity, the special theory of relativity and the general theory of relativity, which were developed in the early 1900s. And the basic idea of a black hole in Einstein's theory of relativity, and this is really our modern understanding of black holes, the basic idea, I would say, is really captured by the one I told you here. There's a lot of interesting things that are not captured by this idea, but the core concept is there. One sort of wrinkle that shows up in Einstein's way of thinking about it is that in Einstein's theory, it turns out there's no pressure in the universe large enough to counteract gravity if you make the object smaller than this size, where the escape speed is larger than the speed of light. If an object is that small, gravity wins out over all other forces in the universe, causing the object to collapse entirely in on itself. All of the matter, we think, collapses to the very center, the little red dot in the image there. We don't exactly know what goes on right there at the center, and I can come back to that in questions if people are interested. The event horizon, this radius that we estimated following Michel and Laplace, a few miles for something that has the mass of the sun, in Einstein's theory, this is really the point of no return. If you're outside the event horizon, you can get out if you can travel nearly the speed of light. But if you're inside the event horizon, nothing can get out. And the reason nothing can get out is that according to Einstein's theories of relativity, nothing can travel faster than the speed of light. And so if gravity is so strong that not even light can get out, then nothing can get out. And so normally when we talk about the radius of an object, the radius of the sun, the radius of the earth, I think you know what I mean when I talk about the radius of the earth. It's the thing we stand on. Okay, it's not the podium, but it's the crust of the earth that you stand on, where the material transitions from being a solid to a gas. There's stuff there, you're standing on it, right? That's the radius of the earth. Black holes are weird in that there's actually nothing there at the event horizon. The radius of a black hole is really defined as this point of no return. Inside of that region, everything is forced to fall into the center. Outside of the event horizon, in principle, if you can travel at nearly the speed of light, you can escape out to the rest of the universe. And so the radius of a black hole is really defined in terms of how material can travel or how information can be communicated. This idea that once you're inside the event horizon, everything gets sucked into the center, this leads to what I think is the single biggest misconception about black holes that are out there in popular culture, largely because of science fiction. And that's that you should really go home tonight and have horrible nightmares about being sucked into a black hole because everything gets sucked into the event horizon and falls into the center. That's not true. Okay? Black holes are not actually a cosmic vacuum cleaner. I've tried to emphasize this by using every keynote tool at my disposal, including one I didn't realize until last night, the bounce feature. The key point here is that when you're far away from a black hole, way far away from the event horizon, then Newton basically got it right. Gravity is the same for a black hole as it would be for any other object there that has the same mass. So just like you don't need to have nightmares that we're going to fall into the sun tomorrow, you don't need to have nightmares that there's some black hole out there that we're necessarily going to get sucked into. Because far away from the black hole, gravity is essentially what Newton predicted. So to highlight this, if you got rid of the sun and you put a black hole in its place, and the black hole had the same mass as the sun, then gravity would be the same, and the orbit of everything in the solar system, the planets, the moon, the asteroids, would be the same. Lots of bad things would happen, but all of the bad things would be because we rely on the heat of the sun to have life here on Earth. Okay? Gravity wouldn't change. So it's only when you're close to the event horizon that gravity is fundamentally different and all these interesting things happen. And what's so amazing about this picture I showed you at the beginning of the talk, and that we'll come back to, is that that's a picture of the region very close to the event horizon where all the crazy things happen. Okay. So now let's move to try to actually find some black holes and study them. That's not so easy. That's a real picture of the night sky. There are places on the sky that look dark, where there doesn't seem to be much light coming from. most of those regions are not black holes. They're just regions where there aren't any stars, or in this case, there's actually a bunch of junk that's blocking the light of all the background stars. Okay. So finding black holes is more challenging than just looking up at the sky and finding a place where there isn't any light coming from there. We have to be a little bit more clever. And there's actually different ways of finding black holes. Astronomers have been studying black holes in detail now for 40 or 50 years. We have different techniques for finding them. The one I'm going to focus on is the one that's actually, at first, going to sound completely paradoxical to you. And it's that black holes, objects that are defined by the fact that they cannot on their own produce light, black holes are actually the source of the brightest sources of light we know of in the universe. That doesn't register. So let me show you a couple of examples. This is the galaxy M87. That's the galaxy there. You might not be able to tell. That's about 1 trillion stars right there. From the very center of that galaxy, there's actually material that's being flung out at nearly the speed of light in this linear feature you see here called a jet. That jet lights up, producing light that we can see. And we think that that material is flung out. That's material that almost got into the event horizon, but before it made its way in, it got flung back out again. We'll come back to how that happens. So that's material that almost made it down to the black hole that's at the very center of that galaxy, but it got kicked back out again at nearly the speed of light. This is another example. On the left here, you see what actually sort of looks like a star. It looks like just a bright source of light. But if then astronomers go and they very, very, very carefully subtract off that bright point source of light, you see some faint fuzz around it. That faint fuzz is the light from about 1 trillion stars. There's a single region at the center of that galaxy, a region no bigger than our solar system, that is producing more light than all of the trillions of stars in that galaxy. And we think both of these amazing phenomena are caused by big black holes that are at the center of these galaxies. So how is it that objects that are defined really by not producing light can somehow be associated with the brightest sources of light in the universe? These are called quasars or active galactic nuclei, these incredibly bright sources of light in an extraordinarily small region, less than the solar system in size. What we think it is all associated with gas falling into the black hole. So this is not a real image. Okay? See the caveats? Okay? This is an artist's conception, a sort of schematic diagram of what the region around a black hole might look like. I'll show you some real computer calculations of what it looks like in a second. That's supposed to be the black hole. This is material swirling around the black hole. As the material swirls around the black hole, some of it spirals into the black hole, falls into the event horizon, and is lost forever. Some of it is flung out in one of those jets that you see in a real image here on the left. Okay. So what's special about black holes, we think this process of gas spiraling onto a central object, this is a process known as accretion in astronomy. This happens all over the place. I do a lot of my research on this accretion process. You can have gas spiraling into a normal star. You can have gas spiraling into a black hole. You can have gas spiraling into a galaxy. What's special about black holes is that gravity is so strong that when gas is spiraling into a black hole, it moves at nearly the speed of light. And material, as it's spiraling in, moving at nearly the speed of light, that material gets extraordinarily hot, and hot material produces a lot of light. The sun is much brighter than the Earth. The sun is much brighter than Jupiter because the sun is much hotter than Jupiter. So why does this get hot? It's not because of nuclear fusion. That's what keeps the sun hot. Instead, it's actually something that you're even more familiar with in everyday experience. It's friction. Okay? It's that different parts of the material as it's spiraling in are moving at different speeds. So what happens when you rub your hands together? Your hands are moving relative to each other at different speeds. They get warm. How are Boy Scouts taught to make fire? You rub sticks, you create some friction, that generates heat. Exactly the same principle is operating in this gas spiraling into the black hole. The difference is that the gas is moving at nearly the speed of light. So when you have friction and stuff is moving so fast, it generates a huge amount of heat, which produces this extraordinarily bright source of light. So that's the basic way that black holes are actually able to power extraordinarily bright sources of light. It's the gas spiraling into the black hole that ultimately produces the light that we see. Once the gas falls through the event horizon, none of the light can get out, so the light that we see is coming from outside the event horizon. These objects, gas spiraling into black holes, were discovered in the 1960s and 1970s. Soon after they were discovered, astronomers really embarked on a quest, which was to try to look closer and closer to the event horizon, to look closer and closer to this central region where the gas was actually falling through the point of no return. So where do you look? We actually know about a lot of black holes now. How do you pick which one is the most promising one if what you want to do is take a picture of what it looks like close to the event horizon? To figure that out, it's basically a matter of perspective. What you want is you want a black hole that has a very large mass. And the reason you want that is because then the event horizon is bigger. Remember, the event horizon for a black hole that has the mass of the sun is bigger than the event horizon for a black hole that has the mass of the Earth. So you want a black hole that has a large mass, so the event horizon is a big size. But you also want it to be as close to us as possible so that it looks big on the sky. Right? That's what this perspective image is showing. The Eiffel Tower is much further away than the person's fingers, but they look the same angle, they look the same size on the sky because one is much closer than the other. So what we care about in astronomy isn't the actual physical size of the object, if we want to take a picture of it. What we care about is how big is its angle on the sky. So we want simultaneously big black hole and as close to us as possible. It turns out there are two black holes that we know of that are the most promising. One is the black hole at the center of our galaxy, which I'm not going to talk about because the picture of it hasn't been taken yet. That will be coming out, I think, this year. Instead, the one I'm going to talk about is the black hole at the center of the galaxy, M87. So this is, again, a picture of the galaxy M87. It doesn't really look that exciting. It's 1 trillion stars. It's something like tens of thousands of light years across. It has a very big black hole at its center, one of the biggest we know of. The black hole weighs about 6 billion times the mass of the sun. This galaxy is about 55 million light years away, just to give you a sense of scale. These days, that's actually pretty close by astronomy standards. How big is the event horizon? So the angle, okay, the angle on the sky that the event horizon subtends is about 1/billionth of a degree. So let me try to give you a sense. That's really a small angle. So let me give you a sense of that. So remember, a circle is 360 degrees. So take one of those degrees, okay, and divide it by 1 billion. That's the angle we're trying to measure. For comparison, the moon, this is the full picture of the full moon, actually rising over the hills near where I live. The full moon is about 1/2 a degree on the sky. So what we want to do is we want to take a picture where we could see something that's equivalent to seeing something on the moon that's about 1 billion times smaller than the moon. So it turns out that a dime is about 1 billion times smaller than the moon. So the challenge, taking the picture of what's happening near the event horizon of this black hole, The challenge is analogous to the challenge of taking a picture of a dime on the moon, not on the moon, you're on Earth, okay, no cheating. You're on Earth, looking at the moon, taking a picture of a dime on the moon, and checking whether or not the dime was 2017, 2016, 2015. So that's really hard. So thankfully, we have some awesome telescopes. One that you've probably heard of is the Hubble Space Telescope. This has probably taken many of the most famous pictures in astronomy. This is called the Pillars of Creation, one of Hubble's most famous images of where new stars are forming. This is two galaxies that are colliding with each other. So you might think, okay, Hubble has taken these amazing pictures. Maybe this is the telescope to use to take a picture of what's happening near the event horizon of a black hole. It turns out that Hubble isn't up to this task, not because of some current inadequacy of the Hubble Space Telescope, although it sort of is, it's just not big enough, but really it's some laws of physics. It turns out, and this is a bit of a detail, so don't worry about this if it goes over your head, but the angle that you can measure with the telescope depends on the size of the telescope. The bigger the telescope is, the smaller the angle that you can measure using a telescope. And this is related to a law of physics called the diffraction limit, or the fact that light gets bent as it travels through telescopes. It turns out that the Hubble Space Telescope is too small by a factor of 10,000 to take the picture we want to take. So that's bad, okay? Because forget about budgets, right? It's just totally impractical to build technologically a telescope 10,000 times bigger than the Hubble Space Telescope. So how do we do this? It turns out there's a trick. The trick was originally developed in the 1940s, and the modern version of the trick was developed in the 1970s. The trick is that you actually combine the light very, very carefully. Okay? How you combine the light is tricky, but you combine the light from telescopes that are far apart from each other. And then the light thinks that it's all been captured by one super big telescope. So the light comes into this telescope, the light comes into this telescope, and you have to record all of the details of the light as it comes in. Exactly when the light came in. For those who know this, light is an electric field, goes up and down as it comes to the telescope. You need to know exactly when the light wave was up, when it was down, when it was up, when it was down. So you need really good clocks at the telescopes to know exactly when the light came in. So you then freeze the light, like Han Solo in Star Wars, right? You freeze it by recording it onto a hard drive. And then, in your leisure, you FedEx the hard drives together to a common place, and you combine the light later on a computer. So this is the technique of interferometry, and it allows you to create much better pictures than you could make with just one of these telescopes alone. A lot of the work on interferometry was actually done at Berkeley in the 1970s. Hat Creek, California, which is in Northern California, is where a lot of the pioneering experiments were done. This is some of the early version of the experiments that they did. These are the two telescopes that they combined. This is actually a tractor that they used to pull the telescopes around to get them closer together, further apart. The modern version of this experiment, where you take these telescopes in different places, we now separate them by a lot more than 1,000 feet or so. We put them all over the Earth, and we combine the light from all over the Earth. So the modern version of this is the Event Horizon Telescope. This consists of telescopes in Hawaii, Arizona, Mexico, Spain, Chile, the South Pole. South Pole is actually a great place for astronomy. It's not a great place for astronomers, but it's a great place for astronomy. They're now putting a telescope in Greenland to enhance the capabilities of the telescope. And then all of these different telescopes record the light in the way I described to you, and then you later on a computer combine all of the light from those different telescopes to create a picture that's much better than what either of these telescopes could do on their own. And the big technological breakthrough, what really made the picture of the black hole possible, was the completion of a new telescope in Chile called ALMA, which is a very large telescope, so it can gather up a lot of light, and it made the telescope, the Event Horizon Telescope, it made it basically a much more powerful telescope than it was before. This team, the team that does these observations, is about 200 people at 60 universities and research institutions in about 20 countries. I'm actually not a part of the team, so my expertise is in the theoretical modeling, so I make the predictions for what these types of observations hopefully will see and try to interpret the observations when they come out. But this is a huge team, and the results that came out is a testament to the hard work of many, many, many people. So this is the image that they took. They took the data in April 2017. The image was released in spring of this year. I was actually in Princeton for a few months on sabbatical. We all gathered in the auditorium to watch the press conference live. And this is one of the, I think, highlights, certainly of my scientific career, literally getting goosebumps seeing that image come up on the projector for the first time. So just to make sure we're clear what we're looking at here, the color here, my 8-year-old niece who's in the audience asked me, why is it orange? Which is a good question, okay? The orange is not anything related to color here. Orange, yellow, white here means bright, lots of light. The redder here means less light, and black means very, very little light. So really, the color is encoding the brightness of the light. So to tell you what this means and how we interpret it, I'm going to take you through what the theoretical predictions were and how we made those predictions prior to this observation being made, and then we'll come back to the observations themselves. And I do that in part because I'm a theorist, so I like to brag about when the theoretical predictions were pretty good in advance of the observations, and this is one of those cases. So one of the ways that we do the predictions is we actually do computer calculations that describe this process of gas spiraling into a black hole, getting really hot because of friction and producing a huge amount of light. And this is an example of one of those computer simulations that my group has done. So the black thing here is, you guessed it, that's the black hole. The other stuff you're seeing, the color now is encoding how much gas is there at a given place in this computer simulation. What you're actually seeing is basically a donut. So think of this as a slice through a donut, okay? The computer simulation is a full three-dimensional donut, but that's hard to visualize. So we're looking at a slice through the donut. White, there's lots of gas there. Blue, there's less gas. Green, there's very little gas. And the computer simulation now will show you just as a function of time. As time goes on, gas spirals into the black hole. Some of it falls through the event horizon. You can see some of it looks like it's getting flung out. That's material being launched into one of these jets that I showed you the image of, where the material doesn't quite make it into the event horizon, but instead is flung out at nearly the speed of light. These computer simulations tell us where the gas is around the black hole, how much gas is there, how fast it's moving, how hot it is. And with that information, we can calculate how much light is produced at a given region around the black hole. Then we can ask the question, if we were looking at this computer simulation from far away, what would it look like? What would an image of the light from the gas spiraling into the black hole in this computer simulation look like to a distant observer? And in this particular case, it looks like this. So again, the color here is basically showing you information about how bright the light is. So yellow, white is very bright light, black is very little light, and so on in between. This is one simulation and one image. We can do another simulation and make a prediction, and it looks like this. Some differences, but you notice some similar features. We can do another one. Looks like that. and I could keep going. We've done many of these. Other groups have done many of these. You'll notice that depending on the exact simulation, the exact time that I make this mock observation, it looks a little bit different. But there's some very broad features that are present in all of these pictures. There's always one side is brighter than the other, and there's an absence of light from the central region and more light in a sort of ring around the outside. So why is that? So once I explain that to you, I'll basically have explained to you the key features of the actual image that the Event Horizon Telescope took. There's two key things about light you need to know to make sense of this image. What you're familiar with in everyday experience is that if you have a light bulb and you look at the light bulb from different sides, it basically looks the same. It puts out the same amount of light in every direction. Amazingly, that's not true if the light bulb is moving really, really, really fast. Okay. In particular, if the light bulb, or whatever is producing light, the gas spiraling into the black hole, if the light bulb is moving in this direction at close to the speed of light, then it turns out that if you look at it here, it looks way brighter than if you look at it from this side, or from this side, or from this side. And the way we kind of describe this is we say that the light is beamed in the direction of motion of the source of light, the light bulb in this case. So this may sound weird, but you're actually familiar with a very related piece of physics from your everyday experience. So that's a car horn driving past you. Notice how the pitch changes, okay? It goes from higher pitch to lower pitch at some point. Why is that? That's because the car is coming towards you, and then at some point it reaches you, and then it starts going away from you. And the properties of the sound that you hear are different when the car is coming towards you and when it's going away from you. That's what we call the Doppler effect in physics. And what I'm describing to you here is basically a slightly more sophisticated version of the same basic idea. That the properties that you hear or see depend on how fast the object is moving relative to you. So why is the image brighter on one side than the other? Well, remember I described to you that how is this light produced in the first place? It's produced because there's this swirling disk of material around the black hole moving at nearly the speed of light. And half of that disk is going to be coming towards you like this. The other side's going to be going away from you. This side is brighter because that is the side that happens to be coming towards us when I created this mock observation. This side is dimmer because that's the side that's moving away from us at nearly the speed of light. So that difference in brightness on the two sides is fundamentally due to the fact that the material, the gas spiraling into the black hole, is moving very close to the speed of light. It's moving so fast that the light produced by that gas preferentially goes in the direction of motion, which creates this asymmetry, one side brighter than the other. Okay. The second bit of physics about light I need to describe to you is that the gravity of an object can actually deflect the path of light. Now, this is true certainly for a rock, right? Let's go back to our example. We throw a rock up, it comes back down. That's gravity deflecting the motion of the object. The same thing is true for light. Gravity actually changes how light moves. So this is an example where you have the sun here, the earth here, and a star here. The light seems to be going on a line that would take it over there. But because of the gravity of the sun, as the light passes close to the sun, it gets tugged towards the sun a little bit, and that deflects it towards the earth. And so its path is bent a little bit by the gravity of the sun. And so when we look up at the sky, where we actually would see that star is over here, even though the star is actually there. This is an effect known as gravitational lensing. This was first detected, actually, in basically the experiment I'm showing you here. The bending of light by the sun is one of the famous experiments that confirmed Einstein's theory of general relativity, this deflection of light by the sun. Now, this also happens if you have light passing by a black hole. The difference is that the gravity of the sun is pretty puny compared to the gravity of a black hole. So the gravity of a black hole can dramatically change how light travels. So to show you this, these are actual calculations showing you light coming in. The black region is the black hole. Light is coming in. Each of these rays follows the path that light would travel. So here, light comes in and is bent by actually almost 45 degrees. That's pretty good. This light ray is a little bit closer to the black hole. It gets bent more. This one's a little bit closer still. It gets bent more. At some point, the light gets bent, so it basically starts going out the direction it came from. So basically, the light gets turned around almost like a mirror, and it goes back out the direction it came from. This case is even more remarkable. The light comes in, sort of orbits around, and then goes back out again. Okay. So light traveling close to a black hole, its path is dramatically altered by the gravity of the black hole. If the light rays are too close to the black hole, the light actually gets absorbed by the black hole. So this light is trying its best to avoid the black hole and go past the black hole, right? It's not headed straight towards the event horizon. Here, that's the event horizon. It seems like it should be okay, but the bending of light by gravity causes this light to actually bend in and get absorbed by the event horizon of the black hole. So this is gravitational lensing, bending of light by gravity of objects, and it applies to any object in the universe. It's just, in the case of black holes, those are the objects with the strongest gravity, and so they have the most dramatic effect on light that's near them. So in this image, the reason that you don't see much light from the center, okay, is because that's the region where light is doing this. Most of the light, there is gas close to the event horizon there, but most of that light, as it tries to get out, is bent so dramatically by the gravity of the black hole that it ends up falling into the black hole. So you literally end up seeing a black deficit of light because of the strong gravitational lensing and bending of light by the black hole. The light that does manage to make its way out ends up showing up in this sort of ring-like structure that you see here and that you saw in the other theoretical predictions that I showed you. So what's truly astonishing then about this real observational picture, okay, that the Event Horizon Telescope took, is that it confirmed these basic predictions of Einstein's theories of physics about what happens close to a black hole. Materials moving at nearly the speed of light, one side's a bit brighter than the other, and very close to the black hole, the bending of light is so extreme that light produced outside the event horizon actually ends up being bent, and most of that light ends up falling into the event horizon. And that's why there's this deficit of emission. And so in sort of one fell swoop, these observations tested our understanding of how gas behaves and how light behaves very close to the event horizon of a black hole. Really an amazing set of results. One thing you'll notice is that my theoretically predicted images, shown here, they seem like they have more detail. There's finer structure than in the actual observations, which look a little blurrier. Okay. That's basically a limitation of how hard this experiment is. This is as good as the telescope can currently do. So to illustrate that for you, I'll show you a picture from one of the papers that the Event Horizon Telescope team did. They did a bunch of the type of computer simulations that I showed you. They actually made about 60,000 of these mock images that I showed you 3 of. Okay. I didn't show you all 60,000. I showed you only 3. So these are 3 examples from their paper. And then they said, what would that look like if this were reality and we were looking at it with the telescope, with the current technical capabilities that the telescope had, and this is what it would look like. So the fact that the observations are a bit blurrier than the theoretical models is because the telescopes basically are limited. The furthest they can be apart is the size of the Earth. Okay? Astronomers are, if any, they're very entrepreneurial, so there's now ideas about putting these telescopes in space. And so as time goes on, the observations are going to get better and better and better. And my guess is that on some time scale, 10, 15 years, we'll start having images which actually look more like this as the observational capabilities continue to improve. This is sort of like the first picture we had of the surface of Mars, right, which lacked all of the amazing, exquisite detail of river valleys and everything that we can see today. So this is really just the beginning, not the end of this scientific enterprise. Okay, so I'll end there and happy to take any questions that you have. Thank you.
Hi. Are we looking at the accretion disk edge on or at a different angle? First part of my question. The second one is that image should not be taken as a qualitative appearance of what the accretion disk looks like. Mathematically, it's more complicated, right?
Right. So the question is, if we go back to this schematic, there's this disk of material spiraling in, and what it looks like depends a bit on the orientation of that disk relative to us. And so in this particular case, we actually think we have an understanding of what the angle that we're looking at it is because we know the direction that the jet is coming out of the black hole. That's a measured thing. We're looking at something like 20 degrees off axis. But in one big difference between reality and this particular artist's conception is we think that in the gas spiraling into the black hole in the galaxy M87, it's not a thin pancake like it looks like in this picture. It's much more like a big puffy donut. And so that means it's a little bit less sensitive to the exact angle that you're looking at. So.
Thank you.
Yep. Another question?
Yes, could you please go back to the actual image?
Yes. Oh, okay.
You should have that on speed dial for this, I think. Now, based on your diagram, the light that gets bent into the black hole is going to look dark, but it's bending. So in my understanding is that the black spot in the middle of this image therefore represents an area of space wider than the event horizon itself. And I was wondering if you could tell me how big the event horizon is on that image.
Right.
Where is it?
The radius, so good question. So this diameter is indeed bigger than the event horizon. This diameter is related to, there's a special place, it turns out, around a black hole where if you sent a light ray out, it would travel in a circle and come back to where it started. Okay, that has a radius that's something like about 5 times or so bigger than the event horizon. So, good question.
Thank you.
Yep.
You had the equation up there that showed wavelength divided by the size of the telescope.
Yep.
So, and the size of the telescope is determined on the location, 2 different locations on the Earth. So if you had the same locations, instead of using a radio telescope, you used an optical telescope, now you're dealing with much smaller wavelengths, higher energy, right? Wouldn't that be a better solution?
So the question is, could you do even better than we've done by combining not radio telescopes, which is what this does. The actual observations were taken at radio wavelengths about 1 millimeter or so in wavelength. But if you went to a shorter wavelength, okay, so the wavelength of light is shorter, which would be the optical or the infrared or the X-ray or something like that, in principle, you could get a much better image. There's two issues with that. The biggest one is that it's very, very technically challenging to do interferometry at shorter wavelengths, because at shorter wavelengths, it's much, much harder to measure accurately when the light arrived at the telescope to the precision you need to know whether the electric field was up or down or up or down. So technically, what I'm saying is, for those who know this, it's hard to measure the phase of the light accurately enough at optical or infrared wavelengths. So that is very, very challenging. And in particular, this has never been done. There has been interferometry at optical or infrared wavelengths with telescopes separated by like 100 meters, but not separated across the Earth. That's never been done. The other problem, it is a slightly more practical problem, but it is a relevant one, is that it turns out that the two black holes that are the biggest on the sky, M87 in the center of our galaxy, this is an amazing coincidence. They turn out to emit most of their light in the millimeter, which is just complete blind luck, basically. So they're not as bright in the optical or the infrared, which means it would be sort of a harder experiment to do for that reason as well. So, good question.
Thank you.
Yep.
With this technique, can we image the dimes on the moon, or maybe can we image the solar system bodies, like Phobos, Deimos? Maybe we can have a closer look with high.
Yeah, great question. So can we use this technique to actually image objects in the solar system, to create high-resolution images of objects in the solar system? The challenge with this technique is it needs bright sources that are actually relatively small. So if you tried to look at something like the moon with this technique, you'd be looking at this tiny patch on the surface of the moon, a dime in size, and it would be incredibly faint and it would be completely hopeless. So this technique, I think, actually doesn't work particularly well for objects in the solar system. You can use it on other astronomical objects, but you need sources that are very, very bright, and somewhat small. You want an object whose size is not that much smaller than the sort of angular resolution of the telescope. So good question. Yep.
Yes, hi. My question relates to interferometry, and I was curious, what is it that you need to synchronize? So I see the clocks up there. You alluded to it, I think, a couple of questions back. Is it you only need to synchronize the peaks and valleys of the waves themselves? So it doesn't really matter when each telescope captures those images?
You do need to know when they catch the images. The key thing is you need to be able to accurately measure the exact phase of the light, the peaks and valleys of the light as it hits the telescope.
And then how much data do you need to capture? How long do you need to capture light for
So
stations? And do all those stations do that at the same time?
Right. So the dishes do it at the same time. They do it basically at the same time. And they actually took data for something like 4 or 5 hours. And part of the reason you're doing that is because these are distant sources. They're not that bright. I mean, they're bright, but they're not that bright. So it takes a while to get enough light to see. You also use the fact that the Earth is moving, rotating in 4 or 5 hours. That turns out to help you make a somewhat better image, because it's moving exactly where the telescopes are relative to the source on the sky, and that helps you make a better image. So the kind of, I would say, dream vision now is the idea of having a couple of satellites in orbit, orbiting around, and you orbit every 90 minutes, and so you orbit 3 or 4 times, you take all this data, you've essentially filled in an incredibly detailed image of the object. That's one direction that the field might end up going. Question?
This one's related to time, and as something is crossing the event horizon, and before that, you see in all the movies about the dilation up to the event horizon, but after it's crossed the event horizon, does that dilation just continue till you get to the singularity at the bottom, or what happens inside?
Right, so the question is asking about sort of the passage of time, which turns out as material is falling into the black hole, as measured by us far away, it seems like time is sort of slowing down as the object falls in. So for instance, if you had a laser pointer and every second as, I don't want to do it, as Andy falls into the black hole, every second as he's pressing the laser pointer, sending the signal out to me, what I would measure far away is as he gets closer and closer to the event horizon, the signals would get further and further apart, not 1 second, 1.5, 2, 3, 4, et cetera, as he falls through the event horizon. When you get inside the event horizon, it actually gets a bit more complicated. Everything falls into the horizon, everything falls into the singularity. The time dilation switches character, so it doesn't really continue in the same way because it's already gotten, when you hit the event horizon, it's gotten as extreme as it can in the way it was doing it, and it sort of changes character and how time dilation actually happens. And there's a sense in which the time and space sort of switch character once you're inside the horizon. That's a slightly technical sense in which that's true, but that's actually the change that happens as you go through the event horizon. So,
I must say, I want to hear you may say more about your last answer if you can, even though it wasn't one of the questions I planned to ask, because you've left me in a state of mystery, which will help me fall asleep very nicely tonight. But
okay, you're welcome. Yeah.
But anyway, but let me ask my questions. But if you do have more to say about
Yep.
time and space or switching character, I'd love to hear it. But when you were talking about most of the energy we observe from the region of a black hole coming from the friction of the differential speed to the matter being accreted into the disk or into the black hole, I also had the impression that black holes would have a very strong magnetic field outside the event horizon, and that if you accelerate charged particles through a magnetic field, you get a lot of energy that way. Roughly how much of what we see is because of that?
Right, so I gave you the friction answer and analogy, and that glosses over a lot of details. So what is actually the source of the light that we see here? This is a process of producing light that's called synchrotron radiation. And that's when you have an electron spiraling around a magnetic field. The electron is very hot. It's spiraling very quickly around the magnetic field, and it produces a bright source of light. So that actually is the process that is producing the light, somewhat related to what you were alluding to. What makes the electrons hot in the first place, hot enough to produce that radiation, is the friction that I was referring to.
Last question.
I was told I could throw things at people who asked multiple questions.
Well, I'll take that advisement as I'm falling to sleep thinking about the mysterious answer to the question before mine. But if the sun were suddenly to turn into a black hole and there's no more light, I've got to think there'd be a lot of material close enough to the sun, instead of being blown out toward us because of the solar wind, would be sitting there and then drawn back into the sun and accelerated to high speeds. How much white light would we get and for about how long?
So that's a great question. I've made that analogy about replacing the sun with a black hole many times. Nobody's ever asked that question. So I don't know the answer to that. That's a calculable thing, but I don't know the answer off the top of my head. Good question.
Hi, this is a question I've had for a little while. I don't know much about, and it's not related to taking pictures of black holes, but it's about particle physics. And it's about disproving the idea of a graviton as a particle that exists to intermediate the force between two masses. So if gravitons exist, and if they behave like electromagnetic radiation in that they exchange photons, doesn't that mean that black holes should not be able to exert any gravitational force because gravitons would not be able to leave the event horizon. So, like,
Right, so
does that disprove that specific idea?
So let me give a little bit of context for the question. So our understanding of modern forces like gravity, electromagnetism, is that at the quantum mechanical level, they can be understood as being produced by the exchange of particles. So the electric force, which is actually what's stopping us, stopping my hand from going through the podium, is the electric force. That is associated with the exchange of photons. Gravity is associated with the exchange of a particle that's called the graviton. That's the quantum mechanical particle associated with gravity. We don't really have a complete quantum mechanical understanding of black holes. That would require a quantum theory of gravity that we don't have. But in the theories that we do have, the resolution of your question is that the gravitons are produced just outside the event horizon. They're what are called virtual particles, some of which are produced outside the event horizon. Some fall in, some escape to a distant observer, sort of mediating the force. So they don't, you're right, they can't come from inside the event horizon in a classical sense. And the resolution of that is thinking of them as being produced just outside the horizon.
Really quick follow-up question. I know that.
No.
Okay, sorry, but sorry.
Yeah.
Okay.
Okay.
Could you say a little bit more about mechanisms linking the accretion disk or donut to the jet?
So the question is, what is the relationship in this, again, very schematic thing between the accretion disk and the jet? The basic mechanism is, as came up in a previous question, is actually magnetic fields. So we think what's going on in practice, in real accretion disks and real jets, is that this disk of material has magnetic fields in it. Those magnetic fields are sort of going out of the disk, and the jet material is material that's accelerated out along those magnetic fields. So the magnetic field is sort of the conduit where matter and energy gets transported out away from the black hole, mediated by the magnetic field.
In your presentation, there was just one little diagram showing something labeled a singularity, which to some might be considered an abhorrent notion. One of the questions touched on this.
Yeah.
So what is this thing called a singularity? Is it just a punt because we don't know the physics that's going on there, or has it really been worked out theoretically? What attributes does it have? What kind of particle structure does it have? And what happens if black holes collide?
Right, so the question is about this singularity here. So the prediction of Einstein's theory of relativity, makes an interesting and somewhat surprising prediction. It predicts that all of the matter in the event that falls through the event horizon, if the black hole is not spinning, okay, which is the diagram here, all of the matter ends up at a point at the center. So it predicts that the material gets arbitrarily close together. If it's all at a point, it gets arbitrarily close together. And we think that can't be the complete answer. So this is an interesting case where the theory sort of predicts its own breakdown, because it predicts something that we don't think in reality is likely to happen. This is where a lot of the interest in black holes from a physics perspective comes from, is trying to understand what really happens at that singularity, because that's one of the few places in nature where you have lots of mass, so gravity is important, but it's in a really small region, so our theories of the really small, which are the quantum theories, are important. So understanding what happens there, we think, requires a quantum theory of gravity, which we don't have. So there's not a complete description of what's really going on at the center until we have a better, more complete quantum understanding of gravity and a quantum understanding of black holes. So that's the somewhat unsatisfying but actual state of things right now. There's a huge amount of interesting work sort of in physics departments trying to understand this. For the most part, for an astronomer, we think that that's not very important for understanding what we see when we think about black holes in the universe, because that's all happening inside the event horizon, and we can't see inside the event horizon anyway. So it's very interesting conceptually, very important for physics, but not important for understanding sort of the astronomy of black holes. So that's the distinction I would make. Three more, okay.
So I was wondering, how long do black holes last, and when or if they do end, what do they turn into?
Yeah, great question. So in Einstein's theory of relativity, which is our most complete understanding of black holes live forever. Black holes in Einstein's theory can have any mass, and they live forever. They just sit there. If they're by themselves, they just sit there, you know, looking, well, not like that. Like, if there's nothing there, there's no gas, they'll just sort of be an isolated black hole. It wouldn't look like anything particularly interesting, but it would last forever. It's more complicated when people try to understand quantum theories of black holes. In those theories, there's something called Hawking radiation, which is that black holes actually do lose a little bit of mass very, very, very slowly over time. So in principle, black holes like this billion solar mass black hole at the center of M87, in principle, if you wait long enough, that black hole, if our quantum guesses about how black holes behave are correct, that black hole might eventually disappear. That will take much, 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 much longer than the current age of the universe to happen. What would be left behind is an incredibly active area of debate. Whether there's anything left behind, whether there's some fundamental particle left behind, and I think the jury is really still out on that question, because that again gets back to this, you have to understand the last phases in the quantum mechanical life of this black hole, and we don't really understand the quantum mechanical nature of black holes completely enough to answer that question yet. So,
Okay, thank you.
two more. Okay, one.
Okay, this is sort of a repeat a little bit. I mean, the universe seems to have originated in a Big Bang. And if the Big Bang came from a very small place, it would have to have been a black hole. And if so, how can a black hole, the previous question was how would a black hole ever explode?
So there are two instances we know of in the universe where there seem to be, according to our current theories, these singularities, where matter is incredibly dense, incredibly close together. We need some quantum gravity theory to understand what's going on. One is the center of black holes, and the other is you rewind the clock of the expansion of the universe back to the beginning of the history of the universe at the Big Bang. But that doesn't mean that even though both have singularities, that doesn't mean that the Big Bang actually was a black hole or we're inside a black hole in some sense. In fact, in the expanding universe, you can ask the question at any point in the history of the universe, you can draw a circle and ask how much mass is in that region, and is that region then larger or smaller than the event horizon? And the answer is that there's never a black hole there. So there's a singularity at the beginning, but that doesn't imply that there's so much mass that there's actually an event horizon. So there's a singularity, but not a black hole or an event horizon in the sense that we've been talking about.
How could that be? I mean, it's there's more mass there than in any of these black holes.
Right. So why don't we talk about this afterwards? So again, the models allow you to calculate at any point in the history of the universe how much material is there at a given place. So you can just plop down a sphere and ask, in this sphere, do I have enough mass to collapse to form a black hole or not? And the answer is no. So,
really?
Yeah. So in just the uniform expansion of the universe, you don't have the conditions needed to produce black holes.
Oh.
Now that doesn't, again, we don't understand the singularity, so exactly at the very, very, very earliest time, what happened is still up in the air. But for every time after that, we actually can address that question. Yep.
Hi, thank you for the talk. I'm interested in knowing if it was difficult to get astronomers from different countries to kind of collaborate together on this project, and if there are any future projects that will require the collaboration of the international community.
So that's a great question. That's like a politics of big science question. It's more about sociology. It is a really good question. And the answer is it's actually very hard. And the challenge is that each of these telescopes decides who gets to do the observations based on a peer-reviewed proposal process. So if you want time on ALMA or the Plateau Vallarta telescope or the submillimeter array or whatever, you have to write a proposal to that telescope and ask to have the time, and then they usually tell you, you get this day, you get that day. And so what this takes is an incredibly orchestrated process of putting together a coherent proposal to all of these facilities, telling them that you need the observations on exactly the same time, because remember, the light has to be recorded at the same time, because we need to kind of reconstruct what the light was doing at every telescope at the same time. So it's actually quite challenging. There's also other logistical things which are more mundane but turn out to be a huge pain also, like weather, right? Because you want the weather to be pretty good at most of these facilities at the same time, and that's not necessarily going to happen. So, for instance, they had data a second year where the data just wasn't as good because the weather was not good at some of the sites. So this is both sociologically non-trivial and practically non-trivial for a variety of reasons. So yeah, great question.
Let's thank Dr.